You can open them if you want to read during the session. Okay, I will. Okay, so now we start with an intro. Today I'll be sharing about fuzzing, and because fuzzing now is quite used quite a lot in finding bugs, but actually also outside of security, uh, many software developers also do fuzzing because it is a very useful tool or very useful technique to find bugs without spending too much time to audit the code. Because if we just audit the code, we may not be able to find all the bugs. So the best way to do it is auditing and also having a fuzzer running in the background. Okay, so here we see fuzzing. It is automated software testing technique that provides a lot of random or unexpected data into a computer program. Then we will normally have a way to monitor the behavior of the program for problems such as crashes or memory uh, the, out of bounds access or use after free, so memory corruption. So um, I will skip through some details. I'll just go to the parts that I think are important. So there are some very oh wait, sorry. I will I will share about the not so related things first. Okay, so when we talk about fuzzing, it's not just about binary, but in security, we also have web fuzzing, but I think maybe many people here already know this. I'll just let's just go through quickly, then we can get the idea. Then we can use the same idea for binary. So you see, if you are familiar with pen testing or hack the box, then you know that many times when you want to enumerate a website, you want to see what kind of endpoints they have, then you will use a web fuzzer like wfast or ffuf is also a very popular tool. So what it does is you give it we can give it we can give it the endpoint that we want to enumerate, for example here, and then we also give a word list. So this one here, we give a word list to say what routes to try. Then ffuf, when you give it the word list and the URL, it will try many, and then it will tell us what is accessible or what looks like you have a error 401 means you need authentication. Then the pen tester or the auditor can and know what endpoints what routes to focus on and uh check if there are any problems there. So this one is for web fuzzing, and today we will focus more on binary fuzzing because for web fuzzing, I think that is all that is interesting. There's nothing more already. It's just like that. But for binary fuzzing, there's a lot of things to learn, and there's also a lot of innovation still going on now because you need to keep think of different ways to make the fuzzer run faster or to have as much coverage as possible. And we will focus on these 2 points today. So on coverage and the fuzzing performance. Okay, so here are some of the popular fuzzers these days. The very popular one is called AFL++. It is very actively maintained. You see commits, it seems like they still make improvements over time. And then there's Okay, I'm not very sure what they do. Maybe some are just small improvements. But this one, it is upgraded version of AFL. The AFL is the original version. But, this one, it was made very, very long time ago. I see, eh, maybe even longer ago. Mm. It is one of the first fuzzers that is very effective, so very fast and also uh, can collect coverage very well. And then because it's not very maintained anymore, you see they stopped already. Now this one we have AFL plus plus that is maintained by a lot of community patches and also a lot of improvements. I'll go through some of the improvements if we have time. Okay, and we also have this Home Fast. This Home Fast is also quite popular, but and I'm not sure if there's still improvements, but it seems like still quite actively maintained. Looking at the commits. So today we'll focus more on AFL plus plus, but if you are interested to find out more, you should go and read uh try out this one also. It is, I think, in mm, for big picture, it does almost about the same things, but maybe there are some small details that are different. And then there's Leap AFL, which is a quite new project made by the guys that made AFL plus plus. It is a library, so instead of calling, you see AFL, we just run everything on the command line. But AFL plus plus is a library to and you can I'm not very familiar with this, but it's a library that you can write code in Rust. Not sure who likes Rust here. You can write code in Rust to configure a lot of things about your fuzzer setup. And one last one is Deep Fuzzer, which is part of LLVM project. This one is also very widely used. It's mainly used by Google. If you go and find this open source fast, actually Google, they quite nice. They have this project called Cluster Fast. They have a very big in their data center or in their compute cluster, they fast a lot of open source projects. I forgot where to find the list. There's a lot of projects. Yeah, you see a lot of projects. So quite good. Not bad Google. They helping open source. So the special thing about Deep Fuzzer is you see over here again for AFL or Home Fast, it is we use it by calling command line, the compiling the program with the AFL compiler, compiling our target program with the AFL compiler, and then run it in the command line. But Deep Fuzzer, it needs more work, but it also gives better, like, force you to do more control over the fuzzer setup. So you have to write a function called llvm fuzzer test one input, and then inside here is to call the functions inside the program that you want to fuzz. So instead of fuzzing the whole program, we will discuss in more detail what this means later. But you can see this is the difference. Later we will be more clear about what the differences between these two are. Okay, so here is the fuzzing workflow. You see, there's a first you must decide on the target. For example, you want to fuzz a library, we will look at this one. This one is a guide by GitLab Security Lab. There's some exercises if you want to practice. We will look at activity exercise 1. So for example, you want to fuzz a PDF viewer because you want to see if there's any PDF file that will make this viewer crash or have any vulnerabilities in there. So if you look at the CVSS of this, it is just a denial of service because thing is, if you attended my first sharing on file passing bugs, a lot of times this kind of file parser, it will just be denial of service because you can only send the file and there's not much that you can do. But this is not always the case, of course. There are, if you have a more complex program, for example, a browser, then if the browser passes a file, maybe you can still write a more complex exploit. But that one is, if you're interested, you can check out the first sharing. Okay, anyway, back to the topic here, we will look at this example. So we'll go through this later. Okay, so the first step is to choose the target that you are interested in. Or if you are the software team or if you are the security team, then you already have a program or target that you are assigned to. Okay, then next step is instrumentation, which is quite important because instrumentation is used for measuring coverage. So if you are familiar with software engineering, unit testing, then you have a bit of an idea about coverage. It's the same concept. So when you're doing program software unit testing, then you have to write test case, and the test case has to cover as many parts of the program as possible, so that and that means you have high coverage, and that will show that you have tested a lot of the parts, a big part of the program. If you have low coverage, then means that your test cases don't test enough and you should test more. So the concept is the same for fuzzing. Okay, then next step is creating corpus of inputs because again, it is same as for software engineering. In, we want to have test cases that can test the program uh, in many different ways to make sure that it works in all its different features that it provides. And we have to create a corpus, and then after that, the fuzzer will mutate the corpus to have new inputs. So it's a feedback loop. It will we start off with a corpus of inputs, and then we mutate the corpus to generate new inputs to keep testing the program with new inputs. Then you see this is quite good because this is automated, and you don't have uh so you don't have to create new inputs yourself. So this whole point of fuzzing is to have this automated system to automatically keep trying new inputs to find bugs in the program. Okay, then in the end, you just will check if everything is okay. Okay, so for this one, the in more details, normally when you want to fuzz a program, it is maybe you got see a lot of write-ups before, and then people say, wow, someone write a fuzzer and find 10, 20 bucks in Microsoft library or some program. But a very successful researcher would always, or from a lot of the conference talks and people share, a lot of the work that people shared, they always share that at first they determine which part of the program they want to fuzz. For example, if there's a, li- a library in the operating system, but the library may have many different components. Maybe if you take file passing, for example, maybe you have one part that pass a PNG file, then one that pass a JPEG file. Then the person that wants to test this system will choose a very specific component, for example, the PNG, or over here we choose PDF. And then so that you can narrow down your input to focus on just one part. And then after that, we will give in new input like what we say here, and we will use sanitizers like address sanitizer or memory sanitizer, which I will share more later, to check if there is a bug. Because okay, this one I'll explain more later. So now we look at the very important part of fuzzing, which is coverage, or we will call it coverage guided fuzzing. Because you see, when you compile the program, after you compile the program and you run the fuzzer, when it gives the input, uh, ideally we want to know which code is being tested by the input. So let me show you an example. I forgot to prepare the link, but hope I can find this. Okay, see if I can find. Uh, they got show this one online. Ah, okay, you see, for example, Chrome, they show how much coverage is being has the fuzzer tested. Okay, let's say for example V8. Yes, fast 48% of the lines of code, but there's also a branch keep track of branches because that's how the coverage is monitored. Okay, then for example, we want to see a component. For example, this new JIT compiler, maglev. Then you can see, for example, this one have 100%, but actually this one have just 21 lines and don't have that many code. So it's not so interesting to fast also actually. But you see, for example, this one, code generator. Or actually, let me show you the parts that have bugs recently. This one, uh, graph builder. Graph builder is quite complex. It's 8,000 lines. This one, they have a few bugs last time. See, my left, uh, uh, okay, this one, then you can see the bug report. Forgot if this one is reported by Fuzzer. Okay, this one is not found by Fuzzer because it's eh? Oh yeah. I think it's found by Cluster Fuzz. And it is in Graph Builder. Okay. Okay, so you see this one, you can see how much it is being fast. Which I forgot what. Green color means covered, then orange means not covered. So for a security team or security researcher, is if you see some parts that are not covered, means that maybe there are still bugs. This is because the fuzzer haven't generated inputs that will test these parts that are not covered. Then maybe it's something interesting to look at as a researcher. Then as for security team, the security team has to write prepare inputs that can test these parts to make sure that they are well tested. So this is coverage. Okay, then the question now is how can the fuzzer, what someone say cannot see? It's too small. Oh, okay, never mind, lah. Never mind. Don't need to see the code. Just the color enough already. Okay, okay, so the interesting question now is how does the program measure coverage? Because if when we compile the program will not tell you when the program take run with an input, the program will not tell you what is the coverage, what parts are being ran. For example, for this one, you see this one, the test case is this. It's a JavaScript file. So when the V8 JavaScript engine run this JavaScript file, it will not tell you by default, it will not tell you where run because there's no point for the user to know. But AFL does something special. It will compile this program and add some extra code to measure the coverage and then report them. So that is what instrumentation is. So instrumentation, so instrumentation is to add code into the program that during compilation to collect some information and give it. For example, you see here this example, very simple code, but when you compile with AFL, then you will have this, this one is compiled with normal GCC, then it's just call printf. Okay, just focus on this one. Then now you see, if you compile with AFL GCC, then you have extra function call called AFL maybe lock. So this one is AFL, you will decide to lock the function, lock this part that is being executed. So let me look at a demo. Actually, my Ghidra got problem. I don't know if I can open my Ghidra. I'll try see. Yeah. Oh, okay, can. Okay, so try one example. Uh, um, split tab. Wait, never mind. Okay. Okay, let's say we write a simple program that takes input from command line. Okay, for example, takes input from the command line and then checks. And we have a buffer that is 16 bytes big. Then we want to see if first value is A and second is B, then we purposely do a overflow. Okay, so if I run this program, why no overflow? Okay, wait, maybe don't do like this. Uh, okay, I just copy the input. Okay, and if I run like this, I start with AB, then I give a long string. Why no overflow? Okay, I'm not sure. Uh, Uh, okay, never mind. We just look at the Vidra first. Oh yeah, my bad. Thank you. Uh, okay. Uh, okay. So we look at the what is compiled by the program. Okay, sorry, a bit small, but mm, okay. You see here. Okay, make it bigger. Okay, this is very normal code, just what I wrote just now. Then now I try to compile with AFL. So yeah, AFL clang uh test. Eh, what? Yeah, let me check. Mm, oh, okay. To use this AFL fast. Okay, now then we see AFL. The one compiled by AFL. Uh, okay, you see first it takes longer to decompile because AFL it adds a lot of instrumentation, so it adds new code to the binary. Okay, we come back to this later. Okay, I think it will take some time. Uh, maybe I just open in GDB. Wait, what? Okay, I think Gira failed to decompile. Yeah, failed to analyze. Okay, then I just open in GDB. Okay, sorry, I didn't prepare a lot for this one. Live demo. Okay, but you see, over here we have this sanitizer coverage. So add a lot of new code. Then okay, I wanted to show the graph view, but it's you cannot see. But let me show you. Over here, you see, when you compile a program like this, then it will have a control flow graph. For example, if you look at this code, because the program when it come here, it has two paths to take. One is it will come into the loop, and one is to go out of the loop. So you see, you got two paths to take. So how this is where AFL adds the instrumentation at the end of every basic block. So this one is one basic block, one basic block, one basic block. Then at the end of every basic block, the CLang will add in AFL will add in instrumentation at the end of each basic block to track that this part is there's coverage at this part. That's why you see over here That's why we see they track number of branches. They show number of branches because this is how the coverage is collected. So maybe you ask why they want to only add at the end of branches. So there are some, first is the benefit is we don't want to keep collecting coverage. We only want to collect coverage when uh as little parts points as possible. Otherwise, you'll make the program very slow. Every time you collect coverage, it will slow down the program because it's running extra code. And also have to write to somewhere also. So if you see, if you add at the end of one basic block, you only need to check once. If you add in the middle of here, or it is the same as adding at the end here because the code, the program will go through this whole basic block. And then here it is more interesting because when the program has two basic blocks to go to, like a if else condition or this one, or mostly if else condition, like the one in my example, then the coverage at the end of a basic block will tell us whether it took the if branch or not lah. For example, so you see over here, because we cannot see the graph, but you see the coverage is collected before the jump, before a branch. Same for over here is okay. I think there's some jumping around here, so it's very hard to see. Okay, if you are interested, then you try to open in a graph view, but I guess it's very hard to see in Ghidra because maybe Ghidra cannot analyze this after all the changes. Okay, never mind. Now we go on to the corpus. So you see, what's the point of the corpus? Because so first is remember just now I say the fuzzer, it will generate new input to test the program. But how does the fuzzer know what input to generate? Because if you just generate random content, random bytes, then it's just wasting your electricity. You're not testing anything meaningful in the program. So it's very important that we start off with the initial seed corpus. So just a initial set of data. For example, this one, if you want to fast a PDF viewer, then our initial corpus, you download some PDF files. Because PDF files, they they are the correct format. And the correct format means that, and being in the correct format means that the program will not just error. Because if you give it a random file or PNG file, then the program will not even reach any interesting code that actually processes this. It will just report that it's an invalid file format and then it doesn't test anything already. Yeah, I think this is quite obvious to you all. So we can move forward. Okay, here we come back to this later because this is a very useful tool for AFL by AFL. Okay, so first, so the next very important part of fuzzing, so just now I say the important part is the coverage. So coverage includes mutation because now we have an initial corpus, which is, for this example, a few PDF files. And then the fuzzer will generate new input files for testing. So you do that with a mutator. So the mutator will mutate the input files and generate new ones. So here are some mutation strategies. For example, a bit flip or byte flip. So either you just flip random bits or flip random bytes, then or do some arithmetic mutation. So if you think about it, so it just take some value in the file and then add some value to it. So you think this is quite useful to test for boundary condition, because if you have a PDF file and if one of the bytes in there is to specify a file size, then this one maybe be able to trigger some edge cases that if you have attended the previous sharing, then you might be familiar. And then there are also some interesting values. This one I'm not very familiar. Okay, then for dictionary is also useful for files that for file formats or input formats that expect very specific values. For example, uh, like a XML file, then we want to give it files words that are correct because otherwise it will just error and say parsing error. Because for example, XML or HTML, maybe it'll be useful to just replace head with say meta instead of you replace head with ABCDE, then no use. It will not help anything because it will just treat it as a object or a tag that is not valid. But if you replace with one of these ones, then maybe you can test a code path that processes one of these and maybe you can find a bug. Okay, but HTML is not likely to have bug, just an example. And this one is actually I'm not very familiar also. If you're interested, you should go and read up. Okay, then uh this mutation, let me show you something. I can find the blog post. Okay, so if you're interested, this guy is the guy that made AFL. So he has some blog posts, and if you're interested, you can read. It wrote about what mutation strategy is better or not. Because if your mutation strategy is bad, then you'll just be generating input files that are useless, no use one. Okay, then after your fuzzer mutates the input file and generate new one, then you add to the corpus. So your corpus will be bigger and bigger with more and more new inputs that supposed to test more and more parts of the program. So you see the coverage should keep increasing. The fuzzer will keep generating new input files and we would want the coverage to keep increasing so that we test more and more parts of the program. And at some point, the number of input files may be too big. There'll be too many files already, but maybe a lot of them actually just cover the same parts of the program, go through all the same paths. Then you feel actually it's not very useful to keep all the files that are the same. So AFL have these two tools. First is AFL cmin. It minimizes the inputs. So it just selects some of the inputs that it thinks are the best uh, inputs that can reach the most paths. For example, input that can, maybe for this example again, input that reaches as many functions or as many lines of code as possible. Then another one is tmin, which is it checks all your input files and then it try to find the overlaps. Then if there's overlap, then it just remove the overlapping one. So you see the coverage doesn't change. It just shrinks the file. Either the file maybe removes the file or keeps the file but make it smaller. So you have some strategies to do it. Okay, then we can try it with this XPDF example. I hope it works because just now my VM got some problem and before this one started, I was still trying to get it to work. Okay, we built XPDF with the AFL CLang fast compiler. Yeah. Wait, wait. If you have any questions, you can ask now also when we're waiting. Hmm. Okay. Uh, yeah, I got some problem, man. I don't know why. Cannot use the fast. Okay. I think I didn't set up correctly. So if you are interested, go and check. But let me show you this. Later we go through this. Actually, you can also just look at the screenshots. It's about the same. But now I'll share about this sanitizers. So just now we talked about mutation. Then now we change. Oh, any recommended setup to run AFL plus plus or for fuzzing? If if you want to do fuzzing, you should probably have buy very expensive computer or run on Google Cloud. Because if you run on normal computer, 8 threads, uh, it's very it will not cover many inputs. Or it will be you can only try 8 inputs at one run. Then if your program is already slow, then maybe you try 8 inputs in 1 minute. Then actually you think about it, one day is also just few hundred inputs, not a lot. But you see the cluster fast, I think they have a lot of very, very big. I don't know where to find very big. But my friend tell me that actually they causing the climate change. So they doing a lot of fuzzing and increasing carbon emission. Anyway, if you want to do fuzzing and your setup is not very big, then I think it's still okay because from what I've seen people who are successful, they also don't need very strong setup because they go and only fuzz the parts that are very, very specific parts that they already have feel that there'll be bug or they feel they just want to try. So instead of you see over here, what we do here is we fast a whole PDF viewer by providing the PDF, uh, a few PDFs, and then keep generating new uh, new files. Sorry, not this one. But if you want to be more focused, it is better to only fast a very small part of the program. Then for this, you cannot just compile and run in the background because the you are trying to cover too many at once already. Okay, let's say we look at the source code XPDF, and then I feel like, oh, maybe you feel that the font font part, the font parsing may be vulnerable or may have bug. So you read the code. Okay, this looks like just okay. Okay, not not much to see here. Okay, but the point is you have to find a function that you think might be vulnerable or might be the entry point to a lot of processing. For example, okay, I don't have a good example here. You have to find that and then let your input go in through there. This one I'll discuss more also in the next article. Yeah, I think I have to speed up. Okay, now answer some question. Also, other than Fuzzing 101, are there any other resources? I think after you read all these beginner guides, if you think it's enough already, then I think very useful to listen to conference talks because a lot of them they share a very special technique that they use. Uh, Mm. And you realize that sometimes actually don't need very powerful techniques also, but some of them when they come out with new techniques is also quite interesting. So I think from conference talks you can learn many new things. Okay, I come back to this. Later we elaborate more on the finding a special function to fuzz. Okay, this one I think I cannot do. Okay, so for sanitizer is again to add more code to the program. And address sanitizer is used by all the fuzzers because it will just crash the program when there's memory corruption. For example, use after free or buffer overflow. So let me show you a program that is compiled with address sanitizer. Okay. Mm, now we see. You see the program become very big because what address sanitizer does is at every point is originally. Oh, I shouldn't do like this. Okay, this one we see the before, and then over here we see after. Okay, here before, and after. Without sanitization, and here is with sanitizer. Okay, see when there's buffer overflow, then it will tell you where what happened. There's a read overflow. Actually, no, it's not read. It should be write. But yeah, seg fault. I think it cannot provide more info because I need to compile with debug. Then you tell me, yeah, tell me which line. See, line 4, what happened? Sorry, I forgot to provide this. Ah, okay, you see, error sanitizer, it gives a lot of info. It says buffer overflow, line, on line, this line, 1, 2, 3, 4, 5, 6, 9, 6. And then say, oh, the access at offset 48 overflow. Right. Okay, so in order to have this detection and to check and to give you so much useful output, you have to see what's the difference. Add so much code. The malloc, it changed to its own malloc called ascend malloc, ascend stack malloc. And then when it loads memory, it also have ascend load when it string copy. Okay, string copy it didn't, but okay, I think so. I guess string copy it doesn't need to change, or maybe it will redirect. Not sure about that. But you see that for any load operation, it will add its own ascend load. And for write also, if I modify this a bit, like this, then it will also have ascend store. So it adds a lot. Then you see, actually this thing makes the program run very, very much slower. So fuzzing, there's this challenge of how to make the program still run fast, and that's why there's this improvement that they keep asking me to use with AFL Fast. It say it makes it faster, or it says that it's two times faster. With better instrumentation. So if you're interested, you can go and read how they do it. I'm not very familiar with it, but by having better instrumentation, they make it faster. Okay, then memory sanitizer is for checking uninitialized memory. So sometimes they'll use it together with address sanitizer. Then undefined UB send also quite useful because it can check for signed integer overflow. And then this one I'm not very familiar. Thread sanitizer is to find data risk. Actually, it's not useful for security. You can is even data risk is usually not exploitable, so it is only useful for people writing the program. And then this one is to check for memory leaks, also not security problem. So usually it's these three. If you are interested in thread sanitizer, you can ask me more because I am currently working with it. Okay, so to summarize this whole top part, we have white box, which is not to summarize, but to add on, we have white box, which is with source code, which is what I've been demoing so far. Then there's also a black box, which is you have no source code. So this is what a lot of the security researchers focus on because uh, it's harder. They have to put in more effort. For white box, usually it's just compile with AFL and choose the functions to fuzz or a lib fuzzer. Okay, so now we look at some demo. I will speed up a bit. You see over here, normally when people run fuzzing, they run on Google Cloud with more compute power or a lot more threads. Okay, then setup. Okay, so here there's this concept called persistent mode, which is also a way to make the program run faster and also to just focus on the important parts. Because you see, the program, you don't want to just provide the file and then let it go through all the initialization every time when the program wants to test that file. Okay, so first we look at this example that is not in persistent mode. You see this simple program that just takes a file, open, read, and close. There's no bug, there's nothing special. Okay, then of course the fuzzer won't find anything because there's nothing special going on. Then you see now there's a persistent mode. So persistent mode, it you have to add we have to add a few more lines of code. So here we say that this is the initialization. And then instead of reading from a file, you tell AFL that this one is the test case. So this is the contents of the test case. So we no longer read from the file anymore. And sorry. Oh, you still read from the file, sorry. But no longer read from the command line input. Because this file just now was provided through command line, but now is a test case variable by AFL fast. That will be a bit faster because you don't need to pass the command line. And also, the more important thing is you can run in this loop. So here it say AFL loop. Then you just loop this a lot of times. And this whole part will just keep running over and over. So now the program, if you see Ghidra, if you know a Linux program or any program, process, you always start with libc start main, libc start main. And this libc start bin it does a lot of things to set up the process, load a library or set up memory map. It's very it wastes a lot of time. So we want the fuzzer to only run this part many times. We don't want it to run libc start main many times. Just run one scan already, then this part run many times. Then, but if your program is int main like this, you cannot just keep looping. But if you tell AFL that you want this part to loop, then it will compile it in a special way that provide the test case through here, and then your program here can stay the same in the loop. Okay, here the image not loading. Okay, the question someone asked, is fuzzing only applicable when you have access to source code? So I'm not sure if you asked before I talk about this part, but the challenging part is black box fuzzing when there's no source code. Then you have to come up with interesting techniques to instrument, or some people decide that they don't want to instrument. So it's fuzzing, blind fuzzing with no coverage. If you are confident with your mutator, it will still be not bad because the coverage is to tell you how good your mutator is. But if you're very confident with your mutator, then maybe you don't need coverage. Okay, so according to this guy's experiment, it went from 7.5K to 10K executions per second. So you can run about 1.5 more times, run 1.5 more times different test cases. It's quite good. And this AFL documentation say tell you to use persistent mode. It's very important. Okay, here I will skip this part because I think you can follow if you are interested to learn. He will show how to fast Vim with the AFL. Okay, so before we move on to the next section, I'll go through this AFL output a bit because these are the useful information that fuzzing you get from a fuzzing run. So see how long you run. Okay, these are very basic. And then here cycles. Cycle is to say one cycle is for going through all the inputs in your corpus. So let's say corpus, for example, in this example here, corpus now got two files only, got two files. So one cycle will be two files, but the mutator will create two more files. There will be four. And then the next cycle will be longer because it process four files, tests with four files. And then maybe the four files, they mutate again, but not necessarily all the new mutations will be kept because if the mutated test case doesn't make your coverage higher, then it means that the test case just run it behaves almost the same as the previous test case. Then no point to keep it. It just makes your let you run one extra test case without any improvement in coverage. So then it will throw it away. So maybe let's say now we got 4 PDF files, and then okay, let's say we got 4 PDF files. Then the mutator create a few more. Then you realize that 2B and 4B didn't give better coverage. Then you will just delete them. Then now we got 6 files. Then it keeps repeating. So each cycle will go through all the files. So each cycle will get longer and longer. And then it will tell. So this one is useful because you want to know how big your corpus is. If your corpus is getting too big, then you run AFL, CMin, and TMin to make it smaller. Okay, then next is cycle progress. Is to tell you how far in the cycle are you in. or maybe some runs will time out because the program just hang or take too long. And then you don't want your father to spend forever waiting, so it was just time out. Okay, then this coverage is very important. Tell you, okay, this one is very hard to read because they use this. If you think about it, if they want to collect coverage, you cannot save every single point in the program because then it take up so much RAM. So what it does is uh let me see if I can draw for you to see. Oh, okay. See here. How to draw. Okay, never mind. Okay, so you only have, let's say, an array of 10 boxes. Or a number of boxes. Then when it reaches a branch, for example, look at this example here. When it reach here, then when you want to record coverage, then it will have a small function to calculate this one, the address map to which box. Then let's say map to this box, then you say that, oh, here we collected coverage. Then when you come here, then again, you have a small function to calculate. It's a bit randomized also, but to make it spread out. So maybe this block map to here, and this block map to here, and so on. So in a fuzzing run, it will be bigger. I have a lot more boxes. Then this one is to tell you the density. So if your map is, okay, I also forgot what this means already, but basically the percent higher means you reach more parts of the program that are unique. Okay, then stage is which stage of the mutation. Because you see over here, there's many different fuzzing strategies. So many different mutations. It's just for you to keep track. What stage of mutation are you at? And this one is some interesting statistics. Is to tell you, oh, your new input, favorite item. You see over here, favorite item. It tells you there's one algorithm to decide if an input goes to a very interesting code path. So this one is the favorite items. And this one is more intuitive, is your new inputs. How many new edges did we see? So you remember the control flow graph, new edges. So if you have 1,000 new edges, means that your program go through a lot more code paths and have more coverage, cover more code. This one is not very sure what this is. Level is which, actually I'm not sure. Oh, you can read yourself. Okay, then usually you see just now, this fuzzer, the setup I showed just now is just running on one CPU, one thread. But if your machine got a lot more CPUs, then you should run on all the CPUs. So here is you have a main fuzzer, and then you have all the secondary that will so this one will synchronize with everyone. And then in the end you get a statistic. You can run this AFL WhatsApp, see the same statistics as above. Okay, after you fast, you find a bug, then it's time to see what happened. So here you can list all the crashes. And then the file name is very long, but it's very useful because they tell you the ID, and SIG is the signal. So if you know about Linux, the signal, SIG11 is seg fault, which is memory corruption, which means something you should look at. Then usually what you can do is you open GDB with your program and the file. So that in GB you can see what happened, where did it crash, and then see if it's a vulnerability. Okay, then moving on is onto so it's triaging and maybe exploitation, which we won't cover here. Okay, are there any questions until this point? Is everything clear so far? Okay, then I will move on to the last part. This one, advanced fuzzing, to share more advanced concepts. Okay, just now we asked, can you only fuzz with source code? So here, talk about how to fuzz without source code. So it's called binary only fuzzing. Then you can think it's actually quite challenging problem because how can you add instrumentation without the source code? Because you cannot compile. You have to modify the program, is it? So here, there's this QEMU. I hope you all know what is QEMU. QEMU is an emulator. It's an open source emulator. Then over here is a bit like do extra stuff because we use emulator to emulate the program that already run on this CPU. So QEMU is usually used to emulate other CPU platform. For example, you want to run an ARM program, then you use QEMU. Run ARM program on Intel CPU, then you use QEMU. But here we're using QEMU to run x86 on x86 because they have this thing called user mode emulation that some people they make some patches to collect coverage. So if you are interested to see how it works, you can read this one. This is the guy that did it. Is Aviondo. You can read this. If you have question, you can ask me later also. But I don't have time to go through this, so you can read it yourself. If you don't understand, you can ask me. Okay, but the idea is that for Kimu, because just now you say is to emulate a target on top of a host. So host is our computer, x86, and target is, for example, ARM. Then it needs to translate all the instruction from x86 to ARM. And then you see, when it translate, then you just add, when you translate, then you also just, you can also just tumpang and add some code to collect coverage. So this one, AFL maybe log. So they add it to the bottom of every basic block that they translate. So that is the idea. Okay, then moving on, you see this Airbus SecLab, they show how to use all these advanced techniques. So we'll go through some of them. So here, this is the example that they choose. This one is a fake example, not a real program. It's just inspired. And you see, this is the program. And the vulnerable function that they want to fuzz is this pass cert. So if you remember, actually got some one of those, I forgot, open SSL or what, maybe got this vulnerability. I forgot already. I think I recently, not too long ago, there's about this kind of vulnerability in SSL passing code. Okay, we will go through how we can apply some advanced techniques to make the fuzzing campaign better. So all these things are things we talked about just now. So start off, again, we want to build a good corpus. For this example, they just use OpenSSL to generate a cert, example cert. And then they, oh, they give, okay, I don't know where, never mind. Okay, so if you have many input in your corpus, not just one, like this example, you have 50 certs in your corpus, then maybe you want to start off, it'll be nice to start off running AFL cmin to only keep the input sample, because just now you see here, AFL cmin, it only keeps, it minimizes the input that reaches the most paths. So you only keep the inputs that are very valuable. And then again, we use AFL tmin to only to remove the overlaps so that we only keep the unique ones. Then with less overlapping and less useless inputs in the initial corpus, then we can make the mutations more effective because we don't just repeat or mutate files that are not very useful in the first place. Okay, so at the start, AFL Kumu, like I shared just now, they translate, then they instrument all the basic blocks. So according to their experiment, this guide, I'm not sure if they got so. Okay, they didn't show. But later it show that there are ways to make it faster. So first is here. You can tell AFL where your program starts and where your program ends. And this one you have to go and find out with a disassembler. And they're telling where to instrument. Wait, people call me. Okay. So we don't want to instrument everything. Maybe you only want to instrument the interesting function. For example, only instrument the parsing function or the component or the file that you are interested in. Then you tell it the parts to instrument. Because there are some parts like the initialization or open the file. This all you instrument also no use. There will not be bugs there. You're just wasting time. So you only instrument the interesting parts. And then next is we understand a bit how AFL works. So they have this thing called a fork server. Because the program is just one program and then it will keep forking. So not sure if everyone is familiar with forking, but in Linux, if you fork a program, means you duplicate your process into two. And forking is actually quite slow. Forking is you have to copy everything from the current process to the new process. So, and there's some setup. Okay, there's not much setup. You just copy. You don't need to run the setup in libc start main anymore. So in this way, it is faster lah. You don't have to run libc start main, but you have to copy everything. Then later you see how we can make this faster without forking. But AFL by default it will do forking, so they don't have to keep starting the whole program over and over again. Okay, then similarly here, maybe you can change your forking to start later because we want to only fork after we finish the initialization. If not, if you have a program that forks before your initialization, let's say, yeah, it's your init and then pass cert. Then if your program forks over here, then every time the new process have to run the initialization, but actually it's not necessary. Maybe for your case, it's not necessary to initialize every time. Instead, if you put the forking to start before parse cert, then we skip this overhead. We don't have this overhead anymore. So this is another improvement. So you see here, it says change the AFL entry point to the start of the parse cert function. Then you see the improvement, it goes up so much, 150 times. So if your fuzzing speed is slow, don't just go and buy more expensive compute. But first, go and think about how to remove all the redundant steps. Okay, next one is persistent mode again. You see, is to avoid calling fork because the fork you can skip the initialization, but you still have to copy everything over to the new child process, and that is not really good. So this one a bit more complicated, but it is same concept as the one seen here just now. But here the difference is here we got source code, so you can tell AFL where is the persistent mode, where is the loop. But without source code, then you have to tell it the address, tell it where to start and where to end through these environment variables. It's the same concept. Okay, then another one is called in-memory fuzzing. So there's another overhead which is reading the file. You see your pass cert, it reads the file, and this read file will fopen. And all these file IO operations it wastes a lot of time. Any system call will waste time because it is not computation. You have to wait for the operating system to give you the file. So when fuzzing really try to avoid having all these system calls running over and over again, if you can, just make it run only once. So what in-memory fuzzing does is you can skip the reading from file, but read directly from the fuzzer's memory. Because if you think about it, the fuzzer, when it do the mutation, it will mutate and then it will save into a file. And then if save into the file, then after that you load from the file again to fuzz. But actually it's the same program that is writing to the file and then loading again. So quite wasteful if you write and load, write and load. It's by the same program anyway. Then you might as well keep it don't write and don't write to file and don't load. Just use what is already in memory. And this one think you have to read this. I think you have to read more. I also not very familiar with this, but that's the concept of in-memory fuzzing, and that's also leap fuzzer. So just now I say, leap fuzzer is good because when you can provide the data directly to the function that you want to fuzz, so you don't read from file anymore because reading from file is quite waste of time and gives a lot of unnecessary overhead. So leap fuzzer, it forces you to do this, and if you can, then it's very beneficial. It gives you a good interface to do it in memory fuzzing also. Okay, this one I'm not very familiar. If you're interested, you should go and check it out. This one, you should pay attention that it might impact your corpus because if you think about it now, your file is not safe anywhere anymore. So originally the certificate file generated by OpenSSL is in base64 format. If you see the SSH public key file before, so normally it will be passed to base64 decode. Then you see, this part is really waste time because your fuzzer, your mutator will mutate and then base64 encode, save in the file, then load, then base64 decode. We just skip all these parts and we just come directly into pass cert buff and then don't need to base64 decode anymore. So just start from here directly and the mutator, whatever it generates, come into this buffer directly. We skip a lot of unnecessary steps. Then, even better now, you can run 25,000 times as compared to at the start, just 18 times. Okay, so this one is all about execution speed, how to use all these techniques. So the thing here is the useful idea here is that you must know what the program does. If you don't have source code, then you'll need to reverse it to know which parts are the just the setup. Then you must skip them. And then now we talk a bit about mutators. So grammar aware mutator means, so grammar, it means the format of the input, because if you are familiar with compiler stuff, then usually they always say grammar. JavaScript, the programming language grammar is what is the correct format of the programming language. Or if you talk about a simpler language, then very simple. Just have a bracket or have number or character. So it depends on your input. So everything, there's a grammar to the input, or if there's a grammar to the input, then it'll be useful to have a grammar aware mutator. Because what this means is not every input is valid. Only a certain set of inputs are valid. For example, for JavaScript, if you give a JavaScript code that will have compilation error, then no use already. It will just give error. Then you waste time only. So it's like that. So if you have a grammar aware mutator, later I'll show a bit more examples. If you have a grammar aware mutator, then it will generate, you can use it to make it generate input that is valid. So for example, for this certificate example, is a X509 format. Is in this ASN.1 format. So there is a grammar to it. There's a format that it must follow. Then it'll be useful to write a grammar aware mutator that follows that format. You can read more about how to do that, but this is the concept. Okay, and then last thing is multiprocessing, which we talked about just now. Yeah, so that's all about the advanced techniques. So over here, it is useful to look at more about the different types of mutators. This is what I want to share. So for different targets, it's useful to have think about the different ways to make a good mutator. Like this one, Domato is a DOM file. The DOM is the H, this thing is the DOM, document object model. So it's the HTML structure like this one. Because the JavaScript, the Chromium, they have a DOM parser. I forgot where is the folder. And not this. Yeah, I forgot where, but I forgot which folder is it. This one is used to fast the DOM. If you are interested, you can read about how they do it. It's quite simple one. So you just tell it the grammar. So you see over here. Okay, a grammar is a set of rules in this format. So for example, you have a CSS, means that you must have a selector then with the curly braces, and then the declaration is something like this. So the better your grammar is, another example is like this. So this one less than means if you know URL encoding, you cannot it's a bit like URL encoding, encode the special characters. So this one is to again put them in the correct one, because at least these parts you don't need to fast. If you mutate this part, it's likely to just give a syntax error. You won't pass anything useful. Okay, so got about more. There's a conference talk also, I think. Mm. Oh, yeah, I remember there's a talk, I think. You go and find. Ah, yep. No, not this. Okay, maybe don't have. There's okay. So one more is this Fuzzing is for JavaScript. It's quite cool actually. Is this guy's thesis? He write a whole thesis. This I think everyone should know. A quite famous guy, Salo. He is a master's thesis or what? Very, very impactful project, because instead of generating valid JavaScript code and fuzzing according to the JavaScript grammar, he do one step better. He convert it to an intermediate language, and then he mutate the intermediate language and then convert back to JavaScript code. And then like that, you have better mutation, because over here you change variable name, you change small characters. The meaning of the program maybe don't change so much. But if you change the intermediate language, which specifies more the actual operations like loading, integer, binary operation, call function, then the mutations are more meaningful. Every time you mutate, you confirm will have a new behavior. But if you mutate this kind of strict JavaScript code, maybe you just change here a bit, change here a bit. You don't change so much of the behavior. That's the idea, I think. Then got many different type of mutator modify different things. So if you're interested, you can go read this whole thing that explain. Then over here, he also uh make sure, so this one syntactically correct means that no syntax error, but semantically correct means your program semantically correct means the meanings is correct also. So it's only useful if the program, the mutator generate sample that are semantically valid. I think here I'll use an example. For example, program that raise uncalled exception is semantically incorrect because it's useless. It just raise an exception, no use. So it tries to generate programs that are still useful. Mm. This is all that I prepared. Let me check. Well, one more here. This is another good article. So the last part for today. If you're interested, you can read this, then share how you can make a good corpus and why is it important. And then here they have show you how to create a corpus. So this one, how he learned some ways to do it. But the hard part maybe is to even find your initial corpus, right? So here he suggests something quite interesting, which is to use this common crawl. Uh, so it looks like this. I never knew about this, but this is crawler data from the whole internet. Then from here you go and find all the files that you need to build your corpus. And they say the training LLM also use it. Okay, then here is just sharing how to do it. Okay, then that's all I have for today. Oh, yeah, last one. Sorry, forgot. This one very good also. This is a very interesting topic that I have of one that I read about, and it's so good that I saw in their bug reports. The WebKit developer also tell them your fuzzer is very good, so you can go and check out this. But the idea is called differential fuzzing, which is a very smart idea because this one is to fuzz the JavaScript JIT compiler. Then when you go so deep, how do you even know your mutator give error? Not mutator. Uh, how do you even know the program is wrong? Because when the usually for JIT bugs, it doesn't necessarily crash the program. It just gives you a wrong value. But the wrong value can be used to generate can be used to uh make the JIT compile even code that is even more wrong, and then you can get out of bounds, for example. But usually the bug itself, maybe it just gives you a wrong value and doesn't crash. Then your fuzzer, you remember just now, we need to use sanitizers such as address sanitizer to tell us when the program crash and crash at where. Oh, by the way, for address sanitizer, it is useful because same for normal programs, when there's out of bounds, the program may not crash on because maybe you didn't write to um, return address, or you didn't write to invalid memory location, and then the program will just run normally. It will not crash. Then that is not very good. So address sanitizer, people compile with address sanitizer so that the address sanitizer instrument the program such that whenever you have out of bounds, it will confirm crash. But it makes the program slower because it does all these extra checks to make sure that it confirms crash when you have out of bounds. So you can go and read more about that also. Okay, so for this one, differential fuzzing, for JIT, how to even, it is quite impossible to put address sanitizer or what into the JIT already. It's too deep already. So they have a new idea, not new, but quite smart idea, which is to do differential fuzzing. So they take the two different JavaScript engine, for example, Firefox and WebKit, Safari. Then they let them run the same JavaScript code, and then they observe the behavior of the JIT compiler. Then if they see that two of them behave differently, do different things, then that means that one of them do it wrongly. What then? That might be a bug. Then you can go and investigate more. And really, they go and found a few bugs in the WebKit JavaScript engine. So it's quite impressive. Okay, this is all I have to share today. I hope you all learn new things. Any questions? Oh, welcome. In which field fuzzing is generally helpful? Okay, so this can be a good summary. So we will, okay, I answer this first. For corpus, is this common crawl? But I think it's not particularly for corpus. It's just all the data on the internet, petabytes of data. They use it for LLM training also. It's common crawl. Okay, so to summarize, fuzzing binary is helpful because it is an automated way to test the program. And this is useful when the program is quite complicated and the security team or the security researcher don't have time and energy to go and read every line of code and think about whether there's bug. So it is a, a useful strategy is to reverse until you decide there's a component that looks like might be prone to bugs, and then you start to fuzz that component, let the fuzzer automatically try many different inputs until you possibly find a bug. So it is helpful to save your time. Uh, and actually not maybe not so necessary for security researcher who are doing bug bounty because it is just to save their time, but it's very useful for software developer or security teams because the software team usually don't have time to go and audit their everything and catch every mistake. They have the cluster fuzz to just non-stop fuzzing their programs with many inputs to make sure that it is safe. Yeah, today's recording will be on YouTube, on the M53 YouTube channel. Oh, wait, I think someone asked about internship, but I don't think I can give any help. Maybe other people can give some advice.